All right. So I'm happy we can start perfectly in time. So let me use this opportunity to encourage the remote audience also to ask questions. That's what we are here for. You can type your questions in the chat at any time. We will read them out loud after the talk or in between, as you like. Yeah. So you are heard. So if you need any other information, do not hesitate to ask. I'm now happy to introduce Chatterjee, who will be our next presenter. Until recently, he worked at Google AI, where also this work is based on, right?
That's right.
At Google AI, he was an engineering leader and machine learning researcher. Prior to his time at Google, he was the senior vice manager at 2 Sigma, where he was founding a research group on deep learning in Wall Street applications. And also he led a team for end-to-end FPGA-based trading systems. Before his time at 2 Sigma, he was a research scientist at Intel, where he did performance analysis and formal verification of on-chip networks, and he started his academic career at the Indian Institute of Technology in Bombay. After that, he received his PhD from the University of California in Berkeley. So the stage is yours.
Thank you for that wonderful introduction. And it's I'm so happy to be able to be here in person, and thank you all for attending this talk. Please feel free to ask your questions in the middle of the talk. So just, those who are in the room, please feel free to just raise your hands and interrupt. Those who are online, please feel free to put questions up in the chat. We are not in a huge amount of hurry. So if something is unclear early on in the talk, it's better to ask it then rather than to wait till the end. And, we'll get as far as we get in the time that we have. All right. So my talk today is on generalization and deep learning. And this, as was mentioned, was work done at Google, and in particular with my collaborator there, Piotr Zielinski. And we put up this 80-page paper on this work earlier this year on Archive. And I'll really be going into kind of the details of this work. But to motivate sort of, why this is an interesting question, the fundamental problem today in deep learning theory is what's called the generalization mystery in deep neural networks. And this is essentially the following question: why do networks generalize when they have sufficient capacity to memorize random data? So what does this question really mean? And this was kind of pointed out in this paper from about 5 years ago called Understanding Deep Learning Requires Rethinking Generalization. And this was written by Zhang et al. And they did this amazing experiment. And it was very surprising to many people in the community. Though, of course, other people said that, we have always known that, and there is nothing new here. So the paper got very sort of mixed reception, but the fundamental experiment there was a really fascinating one. And to understand this experiment, think of, trying to train something like a vision model. At that time, I think they were using the inception model on something like ImageNet, or I think they were doing this on CIFAR 10 or CIFAR 100. The blue curve here shows what a normal training loss curve looks like. So it starts from, some sort of loss, and it goes down to 0 as you train, right? But then what these folks did is a very interesting perturbation to this experiment. So instead of training on real data set, on real ImageNet, they trained on ImageNet where the labels were randomized. So one picture of a cat may be given the label of a dog, another picture of a cat may be randomly given the label of, I don't know, a tank or something like that. So they randomized the labels, and then they wanted to see if the network could still fit the training data or not. And to their surprise, they found that the network is still able to fit the training data. And that's this red curve over here. And you can see that it's still able to go down to 0 loss, although it takes a little bit more time. And then they tried lots of different variations of this theme. Sometimes they randomly shuffled the pixels in an image and tried to see if the network could fit the data. Or if they just gave pure random images like random Gaussian pixels, can the network still fit the data? Now, it turned out that in all of these cases, as you can see from this plot, the training loss eventually goes down to zero. So it's able to fit the data. And that is something really remarkable because a lot of the, I would say, the majority of kind of the theory in machine learning of why learning is possible and why generalization happens is based on the presumption that your model is somehow capacity limited, that your model is simple enough that it cannot fit random data or it cannot fit your training set, an arbitrary training set. And therefore, when it fits the real training set, you can infer that there's going to be some sort of generalization. So this goes under the name of VC theory, and there are like lots of modifications to it, including even now people are actively working on improving that theory. But ultimately, this is what was so surprising about this, that neural networks have this capacity to memorize large amounts of random data. And traditional machine learning thinking says that, look, that actually means they should not generalize because they can basically memorize whatever you show them. And yet, in real life, we know that neural networks actually generalize really well. So what's going on? So this is the generalization mystery. And the rest of this talk is going to try and explain why this happens. And hopefully at the end of an hour, hour and a half, you'll get at least some sense of why we think this is no longer a mystery and it can be actually understood. To be a little bit more specific, we are going to rephrase this abstract question of why do neural networks generalize when they have sufficient capacity to memorize random data into two questions. Question one is, there must be something that is the property of the data set that controls generalization. So for instance, here, the blue curve showing the showing the true labels reaches zero training loss or perfect training accuracy. And the red curve with random labels also reaches zero training loss. But in one case, in the blue curve, we know that there is good generalization. On the test set, the model will do well. Whereas with the red curve, we know that on the test set, the model cannot do well, right? It's just random images. It's not going to work. So that means even if we keep everything else constant in our experiment and just change the data set, here images with real labels and here images with random labels, in one case, there is generalization, and in the other case, there is no generalization. So that is kind of question one. So what is it about the data set that can lead to generalization? And what is it about the data set or about some other data sets that doesn't lead to generalization? And the second question is, because all of this training of neural networks happens with gradient descent, what property of gradient descent allows it to find a solution? And a solution here is really a model or some setting of the weights of the neural network that causes good generalization, particularly when there are multiple solutions that fit the training set. So as you might guess, even as this experiment suggests, given a particular training data to a neural network, there are many number of different possible values of parameters of that network that will perfectly fit that training data. But some of these might generalize better or worse than others on unseen data. So what is it about gradient descent that allows it to kind of find the right solution, if you will, that will generalize on unseen data? Both these solutions will kind of give the same result on the training data, but one will do better on test data than the other. So that is the second question that we're interested in. All right. So I don't want to leave you in suspense for like 1.5 hours. So I'll give the answers away right now in the second slide. So why do networks generalize well when they have sufficient capacity to memorize random data? The short answer at a very high level of abstraction is that somehow gradient descent is finding and exploiting commonality between training examples. And intuitively, you can see that that can be a way to answer the generalization mystery, because on certain data sets, you might have commonality between training examples. And in that case, gradient descent would find it, and that might lead to generalization. Whereas on other data sets, like with random labels, you might not have commonality between training examples. And now kind of gradient descent will fit the data, but that's not going to generalize. So that's kind of the very high level answer of what's going on. And to answer these sub questions of what property of the data set controls generalization, The answer is when the gradients of different training examples are similar or if they're aligned. And no worries if you don't understand it right now, what we mean by this, because that's pretty much what the whole talk will be about. And the second thing is, how does gradient descent find a solution that generalizes well? Well, the answer is that in that case, the dynamics of gradient descent lead to models that in the machine learning theory are called algorithmically stable. And interestingly enough, this theory of algorithmic stability is almost as old as the VC theory of machine learning. In fact, you might argue that it's, I'm trying to remember now, I think it's actually older. And it was first developed to understand why nearest neighbors models generalize well, because they also have this capacity to like fit random data or fit whatever data set you give them. But yet in some cases they generalize well and in others they don't. And so we are really going to be applying that other sort of way of thinking about generalization to this problem. All right. So now I'm obligated to say a little bit about what is the connection with resource-aware machine learning. And here I'll give like one half of the answer, and the last slide will have the other half of the answer. So fundamentally, the theory or whatever I'm going to talk about to understand this generalization mystery actually arose from using methods from FPGAs and electronic design automation to understand machine learning, because that was kind of my background, and that's the lens through which I first started sort of trying to understand machine learning. And this was done in a couple of papers at ICML a few years back. So one is on learning and memorization. And there, the main sort of result was that if you try to use FPGA type lookup tables, as the speakers in the previous talk explained how FPGAs work. If you try to use those kinds of lookup tables to do memorization, it actually turns out that even that simple model of machine learning or that simple machine learning model can actually generalize well. And this was somewhat of a surprising thing. And the second thing that we found while doing a detailed like circuit level analysis of machine learning models. So we took some binarized neural networks or highly quantized neural networks, compiled them down into and inverter gates, and then we did some kinds of analysis on them over the training set. We found that neural networks that were trained on random data show more common patterns in a certain sense than you would expect if they were simply like dumb lookup tables. I covered some of this at the topical seminar last year. It was called Using Logic to Understand Learning. And that's when we kind of had the idea of this broader theory that actually has nothing to do really with FPGAs or lookup tables. But now we can use that to actually understand why neural networks generalize when they're trained with gradient descent. So this background is definitely not needed to understand the rest of the talk. So that will be self-contained. All right, so this might be a good time to see if there are any questions. Like, is the problem clear? Like, what we are trying to go after. And if not, like, I'm happy to take some questions there. All right, onwards. So let's start with building some intuition. So our kind of main idea, or the main sort of explanation of how gradient descent, or our main explanation of why the generalization mystery is not a mystery, is to say that gradient descent is going to go and find commonality between examples. Now, luckily for us, gradient descent is a very simple algorithm. And so we can actually try to analyze the algorithm to see how it could possibly find commonality between examples. And so here is a quick recap of what gradient descent looks like. So in gradient descent, we initialize the network or the weights of the network indicated by W0 with some random values. And note critically that this is basically a data independent initialization. So we are initializing the neural network without looking at the training set, just using some heuristics of what the distributions of the weights should be. And then in each step, we update the weights according to this formula down here. And what this is really doing is it is actually computing the average gradient of all the training examples. So the gradient intuitively is the direction in parameter space that you go down in order to reduce the loss. And just think of it as, although in real life we take kind of a discrete step, kind of conceptually we want to take an infinitesimal step in kind of the right direction. And that's what gradient descent is really all about. That we want to find in this vast space of weights, kind of one direction. If we were to go down, the loss should go down. So it's like a, for combinatorial optimization people, this is like a greedy optimization algorithm. You're just trying to find a greedy direction in which the loss would go down. Now, the interesting thing about it is, if we postulate that somehow gradient descent is finding commonality between examples, there is not that many places in this algorithm where that commonality detection mechanism can hide, just because it's such a simple algorithm, right? So in fact, the only place where the examples interact is where we are computing kind of the average gradient or the total gradient, as indicated by this red box here. So this is where we are kind of conceptually, at least, taking the per example gradients indicated by G sub I at the current point in parameter space, and then we are averaging those gradient vectors, and that gives us the descent direction. So if there is some commonality extraction that happens, it must be in this step, and it cannot be anywhere else. So that seems to suggest that kind of this idea of vector addition is where commonality detection lives. And to understand that, like, consider this very simplified picture. So of course, neural networks live in very large dimensions, millions of dimensions, because the weights, the number of parameters of a modern neural network is, tens to hundreds to billions of parameters. But here we are just going to visualize a three-dimensional parameter space. And we are going to look at two examples, A and B. And let us look at their per example gradients. So this is GA, shows the gradient of example A. And this has essentially components along the X direction. So it has one unit along the X direction, one unit along the Y direction, and it just lies in the XY plane. So that's kind of the direction in which you need to move to optimize A. Likewise, the gradient of B has no component along the X direction, but it has components along the Z direction and the Y direction. So if all you cared about was fitting example B, then you would move along kind of this direction, right? Now, when we average the two, we are getting this guy here, G bar, which is going to be just the coordinate-wise averages of these two gradient vectors, right? And now you can see something interesting happens. Because A and B, both, if you move along the Y directions, you can reduce their loss. The Y direction kind of adds up in the average, and you get kind of, a larger component in the Y direction. Whereas, because in the X direction or the Z direction, you are only optimizing one example and not the other, they kind of are a little bit weaker in the gradient is weaker in the X and the Z directions. Does that make intuitive sense? So just by kind of adding the vectors, we are kind of it's some sort of constructive interference that happens in the direction that kind of helps many examples, and that direction becomes stronger. And that is really, I think, the key to this whole thing. So this is just kind of summarizing what I said, which is the gradient is stronger in the common direction that improves both A and B. And remember that the parameters are updated pretty much proportional to the gradients. So the biggest parameter changes that happen are those that benefit both examples, rather than those parameter changes that would have benefited only one example or the other example. All right, any questions on this slide? Like, if you take away nothing else from this talk, I think this is the one slide to remember. All right, any questions online?
So far, no.
Okay, all right, yeah, please.
I take the opportunity to ask a question. Sure. Do you think there is some way to leverage this property even further, like strengthening what is already strong and maybe weakening where differences are?
Absolutely. Like, just hold on for 10 minutes or 15 minutes, we'll go there.
Okay.
Yeah, that's actually, yeah, we'll talk about that. Yeah.
Thanks.
Yeah. All right. So, this is the case when these two examples, A and B, had something in common. So now let us look at kind of a similar setup, three-dimensional space, where they don't have anything in common. So you might intuitively think of this slide as representing what happens with real data, and the next slide as representing what happens with random data, or when your labels are random. So here, the first example, if you move along the x-axis in that direction, you can reduce its loss, but there is no y component here. And for the second example, B, if you move along the z direction, you can reduce its loss, but there is again no y component there. So if you, in some sense, you have to move along different dimensions to optimize each example. And of course, when you add them up, there is no common direction. So what previously was 1 was 0 here. But gradient descent will happily kind of move down this xz dimension, which is the arrow of the gradient vector, and kind of fit both examples. So in the previous case, there was this big common component. Here, that common component simply happens to be 0. But this kind of gives you an intuitive sense of how gradient descent is, the same algorithm is able to fit data that has no common patterns, as well as fit data that has common patterns in a way that will generalize. Okay, so that was kind of a very simple example. And now let us look at a slightly more complicated example, where we'll see that this property, whatever we call the generalization mystery in deep neural networks, you don't have to have a deep neural network to see that problem. You can see that even with linear regression, or more specifically with over-parameterized linear regression. So here we are going to try and fit a very simple model, which is y is w times w dot x. And this is like you have 6 input dimensions, or the input sort of point has like 6 components, and you also have 6 weights. So this is kind of the simple linear model that we are going to fit. And this is the data set that we are going to actually use to train our linear regression model. And in this data set, the first 4 points are the training set, and the last point is the test set. So we'll kind of use that to judge how well we are generalizing, but we won't train with this 5th point. Now, these are the x's and these are the y's. And here you will notice that essentially the x's have some sort of structure here. So the first 5 components of the x's are kind of idiosyncratic components, in the sense that, this, for the first example, x naught predicts what the output y is. For the second example, x1 predicts what the output y is, and so on down the diagonal. But these x's also kind of have a common component, which is this last component, which also directly predicts what the y's are. So this is kind of a very custom data set that we created to illustrate the point. But now you can imagine that you can kind of train, when you try to fit a linear model, you could fit many different linear models to it. You could kind of have a model that kind of uses these signals, to fit the data. Or the ideal model would just use this last signal to fit the data. And you could have any linear combination of them. And now let us see what is the model that gradient descent would find, right? Like, is it going to find the bad model, or will it find the good model? And both of these fit the data. The only question is what would happen on this unseen 5th data point. And now, before going there, we'll create a close copy of that data set where we'll just kill this common signal. All right. So in this data set, which we label M, or you can think of it as random data, you're kind of taking away the ability to use this common signal that kind of works across all examples to fit the data. And you're leaving only the idiosyncratic ones, the ones that are only on a case-by-case basis that can predict what the outputs are. And here also we'll apply gradient descent to see what happens. As you might expect, in both cases, the blue curve here represents what our training loss is. It actually goes down to 0. So we fit the data in both cases. But in the case of the real data set, or L, we actually get non-trivial test performance. So there is some there is good generalization, you could say. Whereas here, in the case of random data, as you might expect, because this common signal is not there, the model will not do well on this 5th data point. And you kind of get bad test performance. So this is kind of, you could think of this as a very simple practical example of the generalization mystery for a very trivial neural net that has no nonlinearities and kind of only the output layer, so to speak. All right. So now we are going to dig into what's going on with gradient descent to see how these two different solutions are found. So the first thing that we do is try to see what the gradients would be in this case, more precisely what the per example gradients would be. And that is what is shown in this table here. And what's interesting is that there is a very specific structure to the per example gradients. This R term is some sort of a residual term and is just a scalar. So, and it's going to be the same for all the examples. And I should be clear, this is gradient descent starting from 0. So there is a lot of symmetry in this problem, which is why, we can write the gradients in this simple form. But here, you can see that the gradients kind of have a very similar structure to the original data set. So each example, like the first example, if you go down this component, you can reduce the loss slightly. So you could use this component to fit the data, or you could use the common component to fit the data. Both, will reduce the loss. And if you were just fitting the first example alone, you would go down some hybrid of the two. Similarly, for the second, this component can reduce the data, can reduce the loss, or this can reduce the loss, and so on. Now, when we add all of that up to get the average gradient, which is shown in the last line, something remarkable happens. So the common one, because it's one for all the examples, becomes 4 times as strong as any of the directions which only help one example, right? And consequently, because before that, let me talk about the memorization case. Here, what you can see is that there is no common component. So you're just left with these, 1/4, 1/4, 1/4 kind of things. But this common direction of 1 is not present anymore. All right. And now, when we actually look at the particular weights and how the weights evolve in time, you can see that in the case of the real data set, the common signal, which is shown in blue, W6, this last guy, or corresponding to the last guy, or this particular input, is the one that grows fastest, as you might imagine, because that's where the gradient is the strongest. Whereas the other ones are moving sort of much slower. And so the overall model tends to have a much stronger, tends to have kind of a much stronger weight on the common part. In the case of random, there is no common part, but the model will still fit the data because each of these idiosyncratic ones, and they're all the same. So because of symmetry, essentially W1 is the same as W2 is the same as W3 and so on. So they're all kind of going to fit the same way, and we'll fit the data. And if you remember earlier, I was kind of telling you that even in the experiments of Zhang et al., they found that on random data, it took them slightly longer to fit the data than real data. And you can kind of see an evidence of that over here as well, that with random data, your training loss is kind of falling more slowly, just because the gradient is so much more diffuse. Whereas with real data, your loss falls much faster because the gradient is so concentrated in certain directions. So you can, yeah, please.
So those plots on the right are the same roughly if you fetch that one? Because then you couldn't use any similarity in the gradients, right?
So that is actually a very, very interesting question. So for the purposes of this explanation, think of it as we are working with full batch gradient descent. With batch size 1, however, something very interesting happens. What happens is, although in any one step, there is no big movement in the common direction, because the common direction is seen for every example, over time, the common direction still adds up. So what is happening in space in the full batch case happens in time in the stochastic case. And later on, when we actually prove the theorem, you can actually handle both these cases uniformly, which is something previous theories couldn't do. So yeah. So it's yeah, that's kind of the reason why even stochastic actually ends up working the same way. But it's interesting to consider already that for a different optimizer like Adam, there might be a much bigger difference between the two. Okay. All right. Any other questions before we move on to the next part? All right. All right. So onwards, and how are we doing on time? Okay, not too bad. I think we might only get through half of this talk, but that's okay. As long as we understand the first half, that's better than not understanding the whole thing. All right. So let's do the first sort of real experimental, or let's drive towards actually measuring what happens on deep neural networks instead of just playing with toy linear models. And our first task is like, this notion of gradient alignment, we call that coherence. Like if all the gradients are kind of pointed in the same way, or they have some large amount of common component, we say that they're very coherent. And we are kind of really using an analogy from physics here, that the per example gradients are adding up in certain directions. And that's why we call them coherent. And our first goal is to try and come up with kind of a mathematical or a quantitative measure for this coherence. And that's what we're going to do now. And then we'll measure it on a real neural network. So if you think about it now from first principles, so we want to understand how well aligned these different per example gradients are. Kind of your first guess to come up with some measure would be to say like, hey, let's just look at the dot product, the pairwise dot product of all the training examples that we have. Or in the language of distributions, we just say, let's look at the expected pairwise dot products, where D is the distribution from which the training set is got. And that's actually it's a really good metric, but it has one big problem, is we can't assign a significance to it. So if I told you that the dot product of two vectors is 18 or 18.3, you have no idea if those two vectors are like very closely aligned or they're far apart, because it kind of depends upon the dimensionality of the space you're in, what the values of the vectors are, and so on. So just seeing a number for the expected dot product does not actually convey any sense of alignment intuitively. So we are going to try and normalize this. And it turns out that there is a very natural normalization factor that's kind of hanging around here, which is the first one here. The numerator of this metric is the expected dot product. But in the denominator, we are just going to scale it by the expected norm of each vector, or each per example gradient. And it might be obvious to you, or it might not be, depending on how often you stare at things like this, that this quantity actually is bounded between 0 and 1. And it's easy to kind of see why, maybe it's not so easy, but the numerator is actually the average gradient's norm. So if you take the expected gradient and take its norm, you would actually get this pairwise product of all the terms in that average on each side. And so in some sense, both of these quantities, and the lower one is clearly the expectation of a norm, so it has to be positive. So both the numerator and denominator are positive. So this whole thing is positive, or at least non-negative. And when the average gradient is 0, that's when alpha is 0. And when all the gradients are perfectly aligned, so imagine that all the gradients are pointing in the same direction, that's when there is no difference between the numerator and the denominator. And alpha takes on the maximal value of 1. So 1 means that all the gradients are pointing in the same direction. 0 kind of means that you have reached the end of optimization. The gradients are such that improving the loss on one example will make the loss worse on another example, or you can't improve the loss on any example. So that's kind of the range of alpha. Now, once we have a metric like this to kind of quantify this notion of coherence, or how aligned examples are, we can now go back and use this framework of algorithmic stability to create or to prove a bound on the generalization gap. And this is going to be probably a little bit dense and technical, but let me just kind of give the high level idea of sort of what this theorem is saying. So the gap here means the difference between training loss and test loss when you take m samples from this distribution D for your training set. And that gap, or the magnitude of that gap, is bounded by some complicated formula on the right-hand side. But it kind of brings together three quantities that are very important to us. The first is the number of training examples that we have, m. So as the number of training examples becomes larger and larger, the gap actually becomes smaller. And this is actually a very good property that it turns out that some of the other sort of theories don't have. So particularly theories based on extensions of the notion of VC dimension and so on up to for neural networks end up having kind of a bad dependence on the number of training examples. So the more training examples you have, it predicts those theories or the bounds there predict that the worst is your generalization. So that's kind of a good thing about this theory, that this appears in kind of a very favorable location for us. The second is this kind of term that we are adding through all the steps of training going from 1 through T. Capital T is the end of training, which you could think of as at any point in training. You know, you could go up to when the entire data is fit or some intermediate location. And what we are really doing there, outside of some constants, which we can skip for now, we are essentially measuring this coherence, this alpha that we measured or defined on the previous slide at a point W in parameter space. So at each of those intermediate points in parameter space, we are going to measure alpha, look at its difference from 1. And so already you can see that if alpha is always 1 during training, so throughout training, if all the gradients are pointing in the same direction, then this term will actually vanish and you won't have a generalization gap at all. So that means your training loss and your test loss will be the same. So it's bringing this notion of alpha in also. And the other kind of important component in training is the number of steps you take for training. So if you take no steps for training, you just, initialize it and stop there. Intuitively, again, you should expect very good generalization gap because you have not looked at the data. So there is no chance for overfitting. So your training loss and your generalized and your test loss should be the same, and the difference in expectation will be 0. So this formula or this bound is actually bringing together 3 very important quantities, which is the number of examples, the number of steps of training, and how aligned these gradients are into kind of one framework. And the only other comment I want to kind of make here is that this notation is hiding something called an expansion factor. And that really relates to the second point, that if you get high coherence early on in training, then that's actually really good for you because that does not increase the bound. Whereas if high coherence appears later on in training, in some sense, the game might be lost. And this is more of a technical point, but we can, we don't need to spend too much time on that now. But it's important to emphasize that this is actually a very weak bound. So if you actually plug in numbers for this, you're not going to get anything non-trivial. And that's a general problem with bounds in deep learning, that some of these constants, we cannot estimate, or our bounds on these constants are so large that these bounds are not very meaningful if you plug in practical numbers. They're much more useful as like qualitative exercises where you're just trying to understand how quantities relate to each other. But that's kind of the general sort of badness of deep learning bounds. But there is also a very specific badness here, which is that this alpha metric itself is a very sort of weak or feeble metric. And we shall see so why later on. And that actually makes this bound particularly useless in practice. All right, any questions here? Please.
Yeah. So alpha is equal to 1,
yeah,
then all the equation becomes 0, right?
On the right side, yeah.
Yeah, so it means that if it is very generalizable, then there is no gap.
There's no gap. Yeah.
So then the thing that actually so it is not given here in the slide. So I suppose that L is the Lipschitz constant.
It's one of the Lipschitz constants, yes, and beta is the other one.
And what are the other constants?
So the neta sub k, that is basically the learning rate at the kth step.
Okay. And beta?
So this thing. So this is the learning constant at the tth time step. And this one is actually 1 plus, so this whole term is essentially 1 plus neta k times beta, the whole raised to t minus t plus 1. So this is like an expansion factor, but that's kind of common in these stability bounds.
And beta is just another constant then?
This one, this sub k?
The beta.
Oh, the beta, yeah, that's also a Lipschitz constant.
Okay.
Yeah. So that actually tells you how much the gradient changes from step to step. So if the gradient doesn't change too much, then you can say something. If the gradient is completely different, because remember, these are very nonlinear systems, right? So if something very different happens with an infinitesimal move, your ability to kind of bound things becomes really small because the space expands. Yeah. So L and beta are both Lipschitz constants of a kind. Yeah. Question?
Maybe you're going there.
to also identify normal fit, for example, architecture search or something like that?
Yeah, I think it can, and that is basically, I think, an interesting direction of future work that we can talk about at the end. Yeah.
And also with the high coherence early training and that, can this also be used for initialization, for example?
That is less clear to me. I think it could, but this actually explains something that people have found in deep learning, which is called adversarial initialization. So it can at least talk about when your initialization can be really bad. So, if you go and fit your initial parameter values looking at the data in such a manner that all the, for example, gradients are pairwise orthogonal, that's a really bad initialization because you have kind of killed coherence. And gradient descent will start from there and happily fit the data, but you won't get good generalization. So people have done experiments like this, and they call this adversarial initialization. But I don't know if it can be used to do good initialization, but maybe.
Yeah, maybe it's also more not so super for the initialization for deep learning, but in other methods like clustering, for example, there is quite impactful.
There maybe, yeah. But we can discuss later. Yeah. Any other questions? All right, onwards. So once we have kind of this metric, the alpha metric, how do we actually go and measure it on a neural network? So on a neural network, in real life, we don't have access to this distribution from which the training samples is got. Instead, what we actually have is just the training sample. And so, we'll kind of measure the same metric on a sample of size m by just looking at the pairwise products of the, for example, gradients and dividing it by the norm. So we'll just use the same formula to measure. And now you could imagine that this set can either be a training set or it can be a test set. And accordingly, you can measure kind of the training coherence or the test coherence. Now is kind of, so far we have seen that alpha must be bounded between 0 and 1, but we still don't have a good scale for it. Like, how close does alpha have to be to 1 for it to be kind of, well aligned? How far away can it be and still be reasonably well aligned? So now we can actually develop the theory a little bit more. And it turns out that there's a very interesting fact here. So if you have a collection of gradients that are pairwise orthogonal, and you try to measure alpha on them, you will find that alpha is 1 over m, where m is the size of the set of those pairwise orthogonal gradients. So the actual gradients don't matter. As long as they're pairwise orthogonal and there are m of them, alpha, in that case, becomes 1 over m. So this actually gives us kind of a scale, because in some sense, a really bad case is if all the examples are pointing in different directions. And that's when you kind of have bad coherence. And so it tells you that if your alpha is kind of close to 1 over m, that's indicative of not so good coherence. And so in practical experiments, what we measure is just this ratio. So how many times better is the coherence that you measure on your training sample or on your test sample compared to if that training sample had comprised of pairwise orthogonal gradients? And in practice, because alpha m perpendicular is just 1 over m, this just involves multiplying alpha m with m. So you just multiply it by the sample size. And intuitively, you can see that this ratio measures how many examples each example has. So this is a little bit of a conceptual shift now. So let's spend like a minute on it. So you can think of each example during gradient descent as helping certain other examples. So if all the examples were kind of pointed in the same direction, each example is helping all m examples in your training set. Whereas if all the m examples in your training set are pairwise orthogonal, each example is only kind of helping itself and no one else. Does that intuitively make sense? So this quantity here, alpha m divided by alpha m perpendicular, is actually, you can think of it as a count. It's telling you approximately how many other examples a particular example helps during gradient descent. If that number is large, that's actually good for generalization, because it means that you don't need to look at all those other examples. If you just go down the gradient given by this example, you're automatically optimizing those other examples. And if that number is low, then you're kind of in a memorization or in a bad situation, that going down the gradient for this example is not helping you with any of the other examples at all. And so you wouldn't intuitively you shouldn't generalize, because if this example were not there in your training set, you wouldn't be making this step. Okay. So now with this particular metric, let's go and actually measure some real life networks and data sets. And so this is showing data for ResNet 50 on ImageNet. And what we have kind of are two rows here. So the first row is what happens on real data, which is real ImageNet. And the second is what happens on random data. And what we did in random data is we just used random images. So we just made the images purely some, Gaussian, each pixel was, picked from some Gaussian distribution that matched the mean and variance of the ImageNet images. Now, the first column here is showing the loss and the training loss and the test loss. And you can see, as expected, the training loss in both cases on real data and random data goes down to 0. But in real case, the test loss also kind of reduces, whereas in the random case, the test loss actually does not go down at all. In fact, it goes up. Same thing, if you look at accuracy, you kind of see a very similar story. So the training accuracy goes to near 100% in both cases. But the test accuracy is only non-trivial in the case of real data. In the case of random data, this is hovering around chance. And in ImageNet, if you remember, there are 1,000 classes. So this number is really 1 over 1,000. That's where this test accuracy is at. All right. So now we're going to go and measure this quantity, which is how many examples each example helps in both these cases. And you can see that in the real case, this number is very high. So at peak of training, around 35 to 40 examples. So you have like a million, and this is, we are measuring it on a sample size of, 50,000 examples. So if you look at 50,000 examples, a sample of 50,000 training examples, you will find that each example in there in real ImageNet is helping about 40 other examples. It's a small number, but it's still, each example is not by itself, it's helping 40 other examples. Whereas in the case of random data, each example is only helping itself, or maybe at most another example, but not other examples. And this last thing is just kind of zooming in on the interesting part of training. So one thing that makes it very complicated to look at random and real data on the same plot, if you're looking at time, is that real data does get fit earlier. So most of the interesting action here in training is happening over here. And then, there is nothing interesting that goes on. So here we just zoom in. And the way we do that is by plotting the loss on the training loss on the x-axis. So if you're looking at coherence as a function of training loss, you can see that for much of the loss reduction phase, coherence is high. So each example is helping many other examples. Whereas for random, even if you zoom in, there is no real coherence there. So on real data, you can actually see this big difference between, you can see this big difference between real data and random data, even with this metric. All right, so that was kind of the good news. And the summary is like, we see much higher coherence with real labels than with random labels. But I think the next slide is going to give us some bad news. So now let's take this, and instead of AlexNet, and I think that will go to your question about architecture and its importance. If you try to do the same experiment on AlexNet, you kind of get a really puzzling result. And at the face of it, it almost like invalidates the theory. So what's happening here is, again, the top row is for real data, the bottom row is for random data. And the first column is for loss, the second is for accuracy. And we are measuring kind of coherence here on the third as a function of training step or epoch, and on the last one as a function of loss. And now you can see in both cases, and particularly in the random case for AlexNet, coherence actually, although later on in training, becomes quite high. So each example is actually helping lots of other examples, even for random data. And you could argue that, well, it's a little bit higher for real than for random. And, it happens later on in training, and the theorem kind of predicts that high coherence later on in training is not as useful as, but, it's kind of disappointing nonetheless. So what's going on here? The problem, and it took us a while to figure this out, is that we were measuring this coherence metric over the entire network, right? So if I go back to kind of the definition of the coherence metric, we are looking at the entire gradient vector. So this is, millions of components, and we are taking the dot product over those entire things. But now we can do a layer by layer analysis as well. So instead of looking at the entire network, we can look at coherence of each layer. And for every layer in the network, we can plot its coherence separately, and we can see what's going on. Is there a question? Yeah.
Yes, so actually, I think is enough further elaboration of what we're talking now. So
yeah.
Does this entail
that
in the worst case example,
the
only thing that I could do to, if I have random data, is to take m equal to 2?
Is to take m equal to 2?
2.
Okay.
Because actually, if I have very distinct data, the only thing that I could do just to optimize the alpha as much as possible is to reduce the batch, the size, as much as possible. So when I'm trained with that batch, is trying to optimize actually that batch. But then as a consequence, by taking n equal to or any kind of low number compared to the overall training size, is that I need to retrain the network with every batch. But that will massively restructure the weights of the network as a whole. So does that entail at the very end that unless there is some kind of generality that underlies the weights that are updated, but in the worst case scenario still, I will fluctuate between different examples, and so I will never reach the local optimum because I can never reach that. Right. So that's actually a good question. So I think it's a bit too long to repeat for the online audience, but maybe I'll try to make the answer self-contained. So a couple of points here. So one is m is actually the size of the training set, not the batch size. Now, even when we are training with random data, because every batch is actually picking a new example, sort of over time, you're making, for every example, you're making very small steps. Instead, if you had actually taken one example and done many steps and then switched an example and done many steps, I think it would be closer to sort of what you're saying, and the network weights might fluctuate a lot. But in real life, because even on random data, even if you set your batch size to be 1 and just take one example, you're kind of overall taking many small steps for each of the examples, and you're kind of interleaving all the examples in your descent. And so it does not really, there is no free lunch here. Essentially, if you have random data, you cannot manufacture coherence in some way. And so you will not be able to kind of get high coherence no matter what you try and get good generalization, unless you do some funky things with initialization, but then of course the theorem doesn't hold. Sorry, this was a long-winded way, but we can have a more detailed discussion offline. So here, kind of as we go back and look at the coherence on a per layer basis, a very interesting sort of image emerges. And again, here the top row is for real data and the bottom row is for random data. And each of the columns here is for each level or each sort of layer in the neural network. And what's interesting here is that in the first convolutional layer, coherence in the random case is actually close to 0 or close to 1, or like this ratio is close to 1. So that means here in the first layer, each example is only helping itself and no other examples. Whereas in the later layers, there is a lot more kind of each example is helping many other examples. And mathematically, you can actually show that the alpha that we measured in the previous slide, which is over the entire gradient vector, is actually a weighted sum of the alphas of all the layers. And that's why kind of it's a very average diluted metric. And so when you measure that, you see a very high coherence because there are layers with very high coherence. But it kind of hides the fact that there are layers with very low coherence. And kind of intuition is that all the overfitting is getting crushed into this first layer. And the other layers are kind of, not doing much overfitting. So the first layer is kind of, bringing all the examples into a common space by overfitting. And then, there is not that much, then coherence automatically emerges at the higher layers. But, this needs to be investigated more. This is kind of just our theory. But to answer, but this also gives some insight into architectural issues, right? Because a ResNet, because of the residual connections, the gradients are much more sort of evenly distributed through the network. And which is why maybe you cannot confine overfitting to one layer as easily in a ResNet as you could in an AlexNet, where the gradient kind of flows from layer to layer to layer. So, I mean, this is all just like guesses at this point. The only sort of real quantitative thing that we have is this big difference between the first layer in the two cases. But bottom line, it's entirely possible that in certain architectures, all the overfitting kind of gets compressed into one or two layers. And so if you're going to measure coherence overall, that is going to be a very weak bound. And so that was the thing for this theorem that I was saying earlier, that it's a rather weak bound, not just because of Lipschitz constants. It's because this alpha is measured over the entire network. Whereas in some sense, what's needed is a much more refined notion of alpha that is almost like the minimum across all cuts of the network or something like that, where you don't want any cut that can overfit and hide low coherence. And that's really what you want to capture in a theorem like this, not this sort of average or gross value like what we are doing. All right, any questions on this part? Yeah, please.
So from this analysis, maybe a good strategy is to select batches early on in training, select batches with the same coherence, like train with one batch cats and dogs and alternating, and then
okay. No, I think if you think about it more, I think it actually argues for the opposite. Yeah, because now what will happen is you might end up overfitting on cats, and this is why this is actually called catastrophic forgetting in neural networks.
But early on the training, then you can switch.
Then you could, but yeah, then I don't know how to think about that. But yeah, that the problem then is that in some sense you're wasting it. Like if you have seen one picture of a cat, you don't need to see other pictures of a cat. You'd much rather see a picture of a dog. And what you really want to find here, again, the commonality here is a common way of explaining that a cat's label is a cat and a dog's label is a dog. So you really want to extract commonality between cats and dogs in a certain abstract sense. So that's why you kind of want to see them together rather than all cats or all dogs. Yes?
Did you try repeating bigger networks?
I think the largest network that we tried was Inception, or actually no, VGG or something like that. Those earlier vision networks, but we haven't tried transformers yet.
So I would contend that the larger network will more likely see that the overfitting.
Oh, I see. That could be. I mean, yeah, that. Yeah. I actually presented this work to him as well. Yeah.
That the overfitting goes away because you pass through the complexity of the path on another downside.
That's right. But here we are always on the far side of his double descent curve. Like in all of these models, we are like way on the other side of it. But there is other theories that the wider the network, the better the generalization, for instance. Yeah, and again, like this way of looking at it. Let's defer that to the end of the talk, because I think that is the direction of future work. Yeah. So anyway, bottom line here is like sometimes you need a more granular analysis, that is layer by layer, to actually understand what's going on with overfitting issues, and particularly to understand sort of how coherence behaves. All right, so now we have about half an hour left, and I think we are doing okay on time. I don't think we'll get through everything, but we'll get through the important parts. We'll just define what we don't get through as not important. So I think I can do that. All right, so this is going to be the second test, and that actually goes back to a question that was asked earlier. Can we somehow strengthen certain directions that are in common? And that's what we are going to do now. So going back to kind of this picture on the right side, that we get from this averaging, and apologies for the notation, but what we are really saying here is just our gradient descent step. So we are saying that the weight in time step t+1 is the weight in time step t,
adjusted by the average gradient. And this J subscript is just indicating the coordinate. So instead of dealing with entire vectors here, we are saying that the jth component of the weight is updated by the jth component of the gradient. That's all we are saying with this added notation. But as you recall, kind of if this was the gradient of one example and this was the gradient of another example, we got this average that kind of had a little bit of the weak components here, which is this half. That was only in one example and not in the other example. And it had a very strong component 1 here, which was common to both A and B. So A and B, if you move down the Y direction, you can reduce loss on both A and B. But if you move down either X direction or Z direction, you only reduce the loss on A or on B, but not both. So we say that X and Z directions are weak here and Y direction is strong. And so if you could manually go in and do surgery, you would say that, look, you don't need to go down this descent direction. You should just go down Y. So, we should just kill this half to 0 and this half to 0 and just go down Y. And that's what we are going to do now in a systematic fashion. So what we'll do is we'll simply, if you have, let's say, 100 training examples, on each coordinate basis, you can look at the distribution of the gradients that you get or the values you get for the gradients of that example. And we'll just get rid of the outliers, some fraction of the outliers. We'll just pretend that they don't exist. So you can think of this as kind of a robust averaging. So instead of just taking the average, we are taking, what we call a vincerized average. So we are kind of getting rid of the tails, and we do this only on a per coordinate basis. So this is not the same as gradient clipping because, we are not doing things across across gradient dimensions, but on a per gradient dimension, we are looking at the values across examples and getting rid of outliers. All right, so we are going to modify SGD in this fashion. So instead of doing this regular averaging, we are going to do this robust averaging. And let's see what happens. So let's go back to our toy instance here. And if you recall, we had kind of the real data set and the random data set. And we had their gradients, which kind of matched this pretty much. So the real data set had a common component in the gradient, and it had these idiosyncratic components. And the random data set did not have a common component, and it only had these idiosyncratic components. So now, instead of taking the regular average, which lets all these idiosyncratic components go through, if we now say that, look, I'm going to eliminate the bottom 25% and top 25% on a per coordinate basis, you see that in real data, all these idiosyncratic components kind of go away, and you're only left with the common component here. Whereas on random data now, you're actually left with no components. So you don't do any sort of descent at all because the only components that are there are idiosyncratic components and there is no commonality. And so you can see that this is kind of one way in which you can reduce overfitting. So by getting rid of the outliers, you just end up focusing on what's the true signal. So now, any questions on this part? Yeah, please. So how do you know how much of the tails to? Yeah. So unfortunately, I don't have a good answer to that question. So in our experiments, we have not looked at practical applications of this. Our goal was just to understand what's going on. So we just sweep that parameter, and this is an example where I'll go into some of that detail. Yeah. So here, any other questions? All right. So here, what we are going to do is, because for this experiment, we need per example gradients. We can't do this on ImageNet because that would be too expensive. We are going to do this with MNIST and a batch size of 100. And for each batch, we will kind of try to eliminate the outliers. So that's what we're doing here. And here, along the columns are various data sets. So the left one is actual MNIST. The right one is MNIST with random labels. Or actually, I think this is with random pixels. So it's 100% noise. And in between are some gradations. So here we have 25% noise. So what does that mean? That means that we take 25% of the images in MNIST and replace them with random pixels, but leave the rest. Okay, so it just gives us a way to kind of explore the space between a real data set and a fully random data set.
And each curve, each of these panels is actually showing 3 different curves. So one is the blue one as before, which is training. Then this orange one which is test, and then an overfit, which is the difference between training and test. And so this is a measure of generalization gap. And because we are doing this noise business, it's better, you can't just look at the difference between these two. It's better to actually have the overfit thing, because we need to make an adjustment. Now, the first row is when we don't, normal stochastic gradient descent is a special case of what we are going to do, because we are saying that there are no outliers. We are not going to remove anything. We are just going to average everything together. So that's we captured that with a parameter called C, and that's set to a value of 0. Now, C equal to 2 means out of those 100 examples that we have in a mini batch, we will get rid of the bottom 2 and the top 2. So each coordinate, you can think of it as we'll sort those 100 values that you get from the 100 examples. And we will get rid of the bottom 2 and the top 2 and average the rest. So that's what gives us this central thing here. And the last one is C equal to 8, which means that the bottom 8 and the top 8, we are going to remove and take the average of the rest. So we are just sweeping the C parameter, and now let's see what happens. The first kind of interesting thing is that on real data, it seems to make no difference at all. So kind of going with a robust average or SGD, there is no difference. And in both, in all 3 cases, you kind of get the same curve as you did with gradient descent. On the other hand, with 100% noise, there is a dramatic difference. So here, in the case of 100% noise, when you just do regular gradient descent, your training curve, the blue line, goes all the way to kind of 100. So you're able to fit random data. But the moment you start removing outliers, so you say that anything that's not common to many examples, I don't want to consider during the gradient step, you lose the ability to fit the training set. And so your generalization gap actually becomes very good. It's 0. And what you see in training is what you get in test, essentially. And for these intermediate values are only shown because essentially, depending on how much noise you have, kind of the more winsorization you need to do, or the C value needs to be higher in order to kill overfitting. So bottom line here, by eliminating kind of outliers, on real data, you make very little difference. And that's kind of good news. This is why SGD works in practice, because in SGD, we are not removing outliers, but yet it generalizes. That's because there is a lot of common sort of directions anyway, and SGD is using that. But with random data, SGD kind of does not find common directions, but happily fits. And by doing this outlier removal process, you kill the ability of SGD to fit the data, or this modified SGD to fit the data. All right. Any questions on this? Okay. So we wanted to see if the same thing would work at ImageNet scale, because MNIST is kind of an unreliable data set. And there, the problem is we can't compute, for example, gradients. The experiments would take forever. So what we instead came up with is something called the M3 algorithm. So what we do is we consider 3 mini batches. And these mini batches could be of size 100 or whatever, some normal or 256. And instead of and then we take the median on a per coordinate basis across these 3 mini batches. Does that make sense? So normally, if I wanted to kind of take, if I wanted to simulate SGD, I would take the average of the 3 mini batches and go down that direction. Here, instead, I'm just taking the median. So that's the only difference between this top row and the bottom. So that's why the top row, we call it M3, which is median of 3 mini batches. And the bottom row, we call it A3, which is the same as SGD, which is just the same thing, but with average. And there again, you will see that on real data, there is not much difference in the 2 methods. But in the case of random data, the regular SGD-like thing where you're taking the average of the 3 mini batches, your training accuracy goes up to 100%. But in the case of where you're taking the median, your training accuracy actually just stays at 0. And that's why you can't kind of see the line over here. So what earlier we did with per example gradients, we do now with mini batches, and the same thing kind of works. And however, this is not a practical algorithm, because you have to do, for technical reasons that I'm happy to get into later on, you have to balance the batch sizes properly so that you collect kind of the right batch statistics, yet it's not so big. Because you can imagine that if your batch size is the entire data set, then taking the median of 3 mini batches does not help you. You know, you'll still kind of, it's taking the median is going to be the same as taking the average, because all of those examples are the same. So, or all of those batches are the same. So there are certain kind of complications here, but the bottom line is that if even at ImageNet scale, if you arrange an experiment carefully, by doing robust averaging, you can stop memorization of random labels, but without impacting what's going on with real labels. Okay, so now in the last like 20 minutes, we'll turn our attention a little bit away from the generalization mystery and try to talk about some other sort of things that happen in deep learning. And one of those questions is, why are some examples learned earlier than others? What do we mean by that? So as any of you who has trained neural networks knows that there is actually a training curve, in the sense that your accuracy doesn't go from 0 to 100 right away, but it kind of slowly grows over time, right? But this motivated a very interesting experiment done by Arpit et al. To see what exactly are the examples that are learned early on in training. Are they constant from run to run? So each time you initialize the network and do a full batch of training, and you look at the examples that actually got learned before you hit 50% average accuracy. Did you learn the same examples early, or each time round you end up learning different examples early, and it's just some chaotic thing? It turns out that there is a lot of order over there. So if you take a neural network and train it, let's say 100 times, you will generally find that the examples that are responsible for this early accuracy in training are consistent from run to run. And so we say that those training examples are easy examples. And those examples, conversely, which are learned later, usually, we call them hard training examples. Is the notion of easy and hard clear? This can be actually quite subtle once you start thinking about it. So let's take a 30-second break. And if you have any questions, let me know. All right. So we now understand what are easy examples and what are hard examples. Now the question is, why does this phenomena happen? Like, why are certain examples easy, whereas other examples hard? And one kind of simple idea could be that there is maybe something special about the gradients of easy examples. You could think that a gradient, easy examples are those examples that kind of have very large gradients, so that their loss goes down very quickly, whereas hard examples kind of have small gradients. We don't know why, but that's why their loss goes down slowly, and it takes more training time to kind of get those examples right. But what we find is that that's actually not the case. The difference between an easy and hard example is not an isolated property of an example, but it is a property of how examples relate to each other. And what I mean by that is, somehow easy examples are the ones where their gradients are more aligned with other examples in the training set. Whereas hard examples are the ones where the gradient of that hard example is kind of off by itself, and the gradients of all the hard examples are kind of off by themselves. And of course, in a low dimensional setting, you might think that there aren't enough dimensions. But in a real neural network where you have 60 million parameters and only 1 million examples, there is like so many more dimensions than examples. So, this phenomena can like very easily happen. And this is kind of our hypothesis, that easy examples are those examples that have a lot in common with other examples. And that class of examples becomes an easy class. And the rest is essentially all the remaining ones that are kind of pointing their own way, and those are the hard examples. And so now, using this notion of coherence, we can actually go and measure the coherence of easy examples. So basically, we create a data set of easy ImageNet images and hard ImageNet images. And we do that simply by sort of counting how many times an example gets classified early during training. And that makes it kind of an easy example. And if it gets classified late in training, then correctly classified late in training, then that's a hard example. And when we measure the coherence, we now actually see a significant difference
between easy examples and hard examples. So an easy example on average is helping like about 50 other examples during gradient descent, whereas a hard example is helping only about 20 to 30 other examples during gradient descent. And then we did this other experiment where we tried to sort of train just a single easy example in isolation and a single hard example in isolation, and see that, does the hard example take longer to train? And it actually turns out not. In our experiments, it wasn't statistically significant difference, but we found that the harder example actually gets trained faster than the easy example if you're just training on that one example. So so in some sense, this notion of easy and hard is actually an emergent property of the training set. Like what all examples are pointing in the same direction, those become easy, and examples that are not are hard. And the other kind of interesting sort of phenomena in deep learning is that it's possible to learn with noisy labels. So your images don't have to be correctly labeled, even if there is some amount of noise. And this is very important in practical applications because, when you send off a data set for labeling, your different sort of, raters or the people who assign labels might not agree, or there might be some noise because, they don't understand the instructions properly or they made a mistake. But we still managed to learn useful models from that. And that is also essentially a particular case of this. And here, I think I'm going to skip the details of this experiment. But essentially, if you have training examples that have correct labels, those correspond to easy examples. There, the gradients are all pointing in the same direction, and they get kind of learned early on. Whereas if you have corrupted examples where images have like bad labels, those correspond to hard examples, and those get trained later, or those get learned later on. And that's why early stopping is a very good heuristic when you're training with noisy labels, because in some sense, a signal is present early on, and once you've captured the signal and you've learned the real labels, you shouldn't kind of keep training and try to fit the incorrectly labeled images. You might as well just stop early. All right, so that's kind of a short detour into some interesting aspects of deep learning that we can understand from this lens. And now comes kind of we are getting back to the main thing, and this is a little bit of a sort of, it's a very important topic, but something that we are only beginning to kind of think about and understand. And this has to do with kind of the role of depth in deep learning and how that plays into all of this. So to get a sense of this, let us start with our old friend, which is over-parameterized linear regression. So here you can think of a linear regression model as a very non-deep model. It's like the one of the shallowest models possible. And if you recall, these were our examples, or this was our training data, and we kind of got these gradients, and these were like the average gradients where we kind of summed up, and we got a strong component in the common direction and weak component in the idiosyncratic. And we found that the weight corresponding to this common part of the inputs, that grows much faster than the weights corresponding to the rest of the, than the other inputs, which are not useful across examples. And we got this test and training curve. So now we are going to take this linear model and we are going to make a small tweak to it to introduce depth. And we do that in a very simple way. So I'm going to take this weight W and I will split it into two things. Okay. So we get a model where that weight actually gets split into W and U, and that I multiply with the input. So graphically speaking, what we have is a model like this. These are our primary inputs. They each gets multiplied with U, and that gets multiplied with a W, and that's gets summed up at the output. So we have kind of just split each weight into two subweights and taken the product. But with this depth, now a remarkable phenomena starts happening. And this starts explaining why neural networks are so much better than linear regression. So here I've tried to show what the gradients are. And now our gradient vector, of course, because we have twice as many parameters in the model, our gradient vector is twice as long. And now there are like two common components here. So you can't read the actual values, but just look at the colors. So there are twice as many idiosyncratic components and twice as many common components.
But what is fascinating is that these components are not independent. So one component depends, so the gradient in the jth component for W depends on the gradient of the sort of Earth component. So essentially, this guy's gradient depends upon the value here, and this guy's gradient depends upon the value here. And that happens for all of this. So there is this feedback loop, and that leads to something very interesting. So the common direction, because of natural coherence, kind of starts growing. There is, that causes kind of, both of these in the first step, the common weights will grow a little bit more than any of these idiosyncratic weights. But then the gradients actually depend upon the actual values of the weights. So in the next step, the gradient of the common thing becomes even stronger than the gradients of the idiosyncratic one. So there is this kind of exponential sort of growth that happens because of the interplay between the layers. And that exponential thing kind of leads to an exponential amplification in the initial parts of training for the common signal. And so in this particular model, you'll actually find, unlike the linear case where the idiosyncratic thing was an important part of the model, here the idiosyncratic weight actually is very small compared to the common signal. It's much stronger here. And because of symmetries, I'm not showing everything, but in principle, from this one graph, you can pretty much figure out every weight or the evolution of every weight in this diagram. And remarkably here, we get better generalization now than the linear model. So here, the training and the test curves are so close to each other that they're pretty much right on top. Whereas here, in the case of linear regression, there was still this gap. So this is another reason why SGD is in practice so effective, even if you're not eliminating outliers or doing anything fancy. It's the common signal kind of has this kind of amplification that happens between the layers due to interaction of gradients between the layers. So this is, this is just to sort of whet your appetite for really thinking about this toy example. Like, it's hard to kind of understand it from one slide, but you have to think about it a little bit, and you will see that essentially this interaction between the layers can greatly amplify any sort of common signal. And this is also related to something that we see in real models, which is for this deep model, the coherence actually increases in the course of training. Whereas in the case of linear regression, the coherence kind of stays constant. But there's a little bit of an aside to show that, how we can also start thinking about understanding the shape of these curves that we see in real training. Like, why does the curve have this parabolic shape? And, why does coherence grow? And then it goes down. The going down, actually, we can explain from the theory, but the growth is, I think, related to depth. Now, one interesting aspect of this is this kind of feedback between the layers can also help with feature selection of intermediate features. And here we have kind of a two-level neural network, and there is no nonlinearities here. So this whole thing is just linear, where we have, in the hidden layer, we have two neurons, one of which I'm going to call the good neuron. So that's this guy. It is connected to all the inputs. And H1 is going to be called the bad neuron because it's not connected to X6, which is the common signal. Our data set is the same as before, this real data set, where we have idiosyncratic kind of components and the common component. So you can think of H1 as, it's kind of, it's not able to see the common signal, so it can only help with some sort of memorization. Whereas H2 is kind of seeing the whole thing, including the common signal, so it can actually try to learn something useful. So in this case also, what's interesting is we find that because of this interaction between layers, for the for W2, which is connected to H2, its weight in the model is much higher than the weight of this other one in the model. And that's when we start both of them from approximately the same point. And this is like 0.01 or something like that. Because if you start them from 0, that's a fixed point and the system will not train. But this tells you that now what happens if we try to do adversarial initialization, that we initially increase this weight a lot more. So we try to force the network to memorize and reduce this.
But for most values of adversarial initialization, so here we are starting it off higher. The bad neuron, we are kind of giving it a higher weight than the good neuron in these experiments. In most cases, the good neuron, even if it starts off with a slightly worse value, because of this exponential growth in its weight, it overtakes it very quickly, and the network kind of learns the right function. It's only when you kind of overpower it by starting this one off at initialization with very high value that this can no longer catch up and your network is compromised. And now we can do the same thing on the entire landscape of values of the initializations of these two weights. And the black regions are where we have good generalization, so that test loss is close to 0. And you can see that most of the landscape is black. And only if you really do this adversarial initialization in certain regions, you kind of get into trouble and you don't get good generalization. All right. And so now this last part of the talk, I think I'm going to skip in the interest of time, but this is essentially a comparison with other theories and sort of an argument for why I think this is the one true theory. But bottom line is that there are certain things that we would like out of a good theory. Like we wanted to uniformly explain memorization and generalization. We wanted to give us insights into why architectures behave the way they do, like why wider networks generalize and so on. Most importantly, a theory should actually say that as we have more training data, generalization should improve. And this was pointed out by in a beautiful paper by Nagarajan and Coulter a couple of years ago, where they went through a list of other bounds, and they noticed that all of those bounds actually were saying that your generalization gap will become worse if you have more training examples, which is not what we see in practice. And so, this is one list of criteria that we need. And to this, we can add other criteria. Like we don't want different theories to say why early stopping leads to good generalization and why training to convergence leads to good initialization. And this starts ruling out approaches based on sharpness or flatness of minimum. Because when you're starting off training, there is, it's not like SGD has run, so you can't say that SGD leads to flatter minima than anything else. So if you're looking for a uniform explanation, that starts ruling out some of these other theories. And then we also know from our limited experience with full batch training that that leads to good generalization. So we don't want to have a very different theory for stochastic gradient descent and for full batch gradient descent. We would like something that is uniform. And lastly, theory cannot be very mathematically complicated because, this community more than others knows that how, we don't really need Lipschitz continuity or any sort of continuity when we are training super discrete, extremely quantized networks, right? Or we have so many different types of activation values and loss functions and so on. So the theory has to kind of work in a very general way across all of these things because generalization is such a broad phenomena. And so we don't want to have a theory that assumes too much mathematical structure of the networks. And to summarize, we think that our approach can actually satisfy all of these criteria of, what a good theory of generalization should be, and it avoids the fatal problems with some of the other approaches. All right. So now in conclusion, kind of, we have an explanation of the generalization mystery that explains a large number of other phenomena as well, like, why some examples are learned earlier than others, why learning is possible with noisy labels, why early stopping works, why we have things like adversarial initialization. It avoids, the somewhat fatal obstacles faced by competing theories. And, this is also a causal explanation that, as we saw with the M3 algorithm or the robust averaging, can lead to new algorithms that can reduce overfitting. So there are many directions for future work. One is work around the theory itself. Like, as I mentioned, I'm not at all happy with this alpha metric of coherence that we have. I think that's like a really weak one. And so can we have a better one with a tighter bound? But we can also use this to try and understand, things like impact of width on generalization, understanding why neural networks actually have something called texture bias instead of shape bias. Like, why do they recognize objects based on color more than shapes? And, can we use notions of coherence to evaluate architectures and see what is a good architecture and what's not? We need to do more experimental evaluation of this theory. Like, we have not tried this on transformers and language models. So I think that's an important one. And there are certain predictions that this theory makes that also should be investigated. And then finally, I'm very excited personally about more practical applications from this theory. Like, can we do hardware acceleration for private learning? So here, because, now instead of doing averaging, if we do things like median and so on, and if we do that in the hardware, then maybe, we can actually have private learning that can be very, very efficient. There is a subtlety here that, this kind of amplification that we do not just leads to better generalization, but it also leads to faster training. And again, it happens because of the amplification that we have seen in the last part of the talk. So not only do you kind of get better generalization, but your training itself runs faster. So your ability to fit the data actually, or you can fit the data faster. And, fundamentally, and this is what led me to this work in the first place, is like, in some sense, can we get rid of stochastic gradient descent altogether and all these, crappy floating point numbers and, all the quantization that we do to get them into 8 bits or 2 bits and, all the added kind of gymnastics that we have to do in resource constrained environments. Because earlier, we didn't understand why gradient descent generalizes. It was somewhat of a magical algorithm. And now what we see is that, well, one of the reasons it generalizes is because it's kind of fitting the data in a way that extracts commonality. So now can we take that idea and do representation learning without stochastic gradient descent in a more sort of, fundamentally sort of discrete way? So I'm thinking of, things like dynamic programming and other optimization techniques to find commonality directly between examples in a discrete model and to do training that way. So this was kind of the second part of, the connection with resource aware machine learning. Is like, it kind of started off, this whole work started off with trying to get rid of gradient descent. And it turns out to be really hard to get rid of because it works so well from a generalization perspective. But now that we understand why it works well, can we actually get rid of gradient descent altogether? Anyway, that's my talk. So thank you so much.
Thank you so much. So we are already getting into the break, but only time-wise, because due to all of these future interesting directions, I would like to give you the opportunity for 2 to 3 questions, maybe, depending on how long they are. There's one.
Is there a relationship between coherence and robustness? Because nowadays this ImageNet-C and all type of benchmarks are coming where the existing architectures fail. Can we comment about robustness from this?
So can you elaborate a little bit more on what you mean by robustness? Because there are many different definitions.
Yeah, robustness, like for example, in ImageNet-C, they blur the images and they distort the images and then say that it somehow misclassifies.
Right. So one notion of it is like, adversarial sort of examples, right? Like where you make a few pixel change to an image and the image of a school bus might be converted into a tank or something like that, right? Like just by, if you flip. So I think, yeah, I believe that in principle, like, through coherence, we can actually understand how adversarial examples arise. And more importantly, actually get rid of them. Because as long as we are like fitting the data without looking at commonality across examples, neural networks will become very, or are very non-robust, right? So for any given image, when it is classified correctly, you don't know if it is classified correctly because it was memorized or because it fit into a general pattern. And by being much more aware through coherence and through other algorithms that are kind of forcing, that are kind of preventing memorization, I think we can generally be more robust. I think that's kind of my thinking on it anyway, but yeah, good question. Related to that, actually, you can also think of the confidence of a neural network, right? So when you're trying to sort of, make a prediction, if you have seen lots of examples similar to that, and if you can somehow track that in the course of training, then you can be much more confident. Whereas, if a particular example has been memorized, it was because there weren't other examples, so you can be less confident. So even if you're not robust, you can maybe somehow indicate a lower level of confidence in your prediction. Yeah.
So you have mentioned that for the median algorithm optimization, one of the drawbacks is the batch size.
Yeah.
And I'm curious, well, we can do something like M3 and we do summation of different medians. Just curious to know what could be the implication of this summation of medians optimization. Have you tried something like this?
So do you mean like
let's say we have like 64 batches.
Yeah.
We do like for each 4 we get the median.
Correct.
We do the sum of.
Correct. Yeah. So that's the thing. So 4 might be too less because you won't get good batch statistics. So remember, all of these have batch norms and things like that in them. So yes, but those are interesting directions to explore. So we only tried standard networks that had batch norms, so we needed at least a certain batch size. The other problem we have is because we are doing these on TPUs, if you have a very small batch size, then your training will take forever. So from that perspective, also you need a reasonable batch size. Yeah, so it's kind of messy, but I think that is where I think there is a lot of interesting direction to make this practical. Like what we have is, you could think of it as a very rudimentary scientific kind of result, but to actually make this into something that works reliably, I think more work is needed. And there are other like deeper problems also with the algorithm. For instance, there is this notion of instability. So because of these like amplification loops, if you are very good at detecting common direction, then you might take huge step sizes that actually make gradient descent unstable. And so there is, in some sense, it becomes a victim of its own success. And normally you can take big steps because your gradient is so crappy. But if your gradient is this like, pure refined thing, then you get into trouble as well.
Okay, so let's thank the speaker again.